Okay, in today's lecture, we're going to cover the first part of our section 4.2 material on null spaces of a matrix. So in general, we're going to talk about two types of subspaces associated with a matrix in this section, namely the null space and column space of a matrix. So let's start by defining what the null space is. So here we would say the null space of an m by n matrix A, which will be denoted as null A, is the set of all solutions of the homogeneous equation A times x is equal to the zero vector. So that is the null space of a matrix A would be the set of all vectors x in Rn such that A times x is equal to the zero vector. So the null space of a matrix A can be thought of in terms of a linear transformation as the set of all vectors x in Rn, which are mapped into the zero vector of Rm by the linear transformation x maps to Ax. So visually, if we have our vector space Rn, and we have a linear transformation T, which is a matrix transformation where elements x are mapped into Rm by the transformation A times x. The null space would be the subset of Rn, so some space within Rn, where these vectors are mapped into the zero vector of Rn. So the set of all vectors in Rn which are mapped onto the zero vector of Rm is called the null space of a matrix. So in our first examples, we'll try to determine whether a given vector is in the null space of a matrix. So let's consider the following. So here we're asked to determine whether the vector w, which is 5, 3, negative 2, is in the null space of this matrix A, which is a 2 by 3 matrix. And to determine whether a vector is in the null space of a matrix, we want to see whether that vector is mapped to the zero vector by the matrix. So let's consider the product A times W. So here A was the 2 by 3 matrix, 1, negative 3, negative 2, negative 5, 9, 1. And we're multiplying by the 3 by 1 vector, 5, 3, negative 2. So we will get back a 2 by 1 vector, where the first entry is found by taking the first row of A with our column vector and taking the dot product of these two expressions. So for our first part of the dot product, we have 1 times 5, and then minus 3 times 3 would be negative 9. So 5 minus 9 leaves us negative 4, and then the product of negative 2 and negative 2 is a positive 4. So taking the sum, we're left with 0. And for our second row, we would take the second row of A and the column vector W and take their dot product. So the first product of the first terms is negative 25 plus 9 times 3 is 27, which would give us 2. And then the product of the last two terms is negative 2. So we have 0. So this is the zero vector in R2. So since the vector W was mapped into the zero vector, we know that W is in the null space of the matrix A. So in the next example, we've got the same vector W, 5, 3, negative 2, and we're asked to determine if it's in the null space of the matrix A, which is this 3 by 3 matrix shown here. So again, let's consider the product A times W. We want to see whether this maps to the 0 vector. So here, A was the matrix 5, 21, 19, 13, 23, 2, and 8, 14, 1. And we're multiplying by the 3 by 1 vector, 5, 3, negative 2. So for our product, we will get back a 3 by 1 column vector, where our first entry is the dot product of our first row of A with our column vector W. So here we have, for the product of the first two entries, 25, plus for the second two entries, we have 63, and then minus 38. So immediately we can see that the entries in or the entry in the first row is non-zero. So this is not going to be equal to the 0 vector. So we can immediately state that W is not an element of the null space of A. If we wanted to calculate the other entries of this product, we could, but it's not necessary. So second row here, let's see, we would have 65 plus 69 minus 4, and 40 plus 42 minus 2. But again, as soon as we see that one entry in this product is non-zero, we know that it could not equal the 0 vector. So it's easy to verify whether a given vector is in the null space of a given matrix. We just take this product and see whether or not we have the 0 vector. Now, the term that we've been using in our definition, null space, is appropriate because the null space is a vector space. So that's established by the following theorem, theorem 4.2 from your textbook, which says that the null space of an M by N matrix A is a subspace of Rn. So equivalently, the set of all solutions to a homogeneous linear system, AX equals 0, which would consist of M homogeneous linear equations in N variables, is a subspace of Rn. So let's see if we can establish the proof for this result. So the first part of this result is to show that the null space is a subset of Rn. So here we could say clearly the null space of A, which is an M by N matrix, would be a subset of Rn, since A is an M by N matrix. So we're looking for vectors that we would be able to multiply by an M by N matrix. And remember that in order for that product to be defined, the number of entries in our vector would have to be the same as the number of columns of the matrix A, which is N. So any vector in the null space must be an N-dimensional vector here. So we've shown that null A is a subset of Rn. Now to show that it's a subspace, there's 3 conditions that we have to check. So here I'll say, let us check the 3 conditions for a subspace. So the first condition is that a subspace must contain the 0 vector. So here we can say clearly the 0 vector in Rn would be an element of the null space of A, since if I take any matrix A and multiply by the 0 vector, I get back the 0 vector. And that's what it means for an element, or for a vector to be an element of the null spaces. It maps onto the 0 vector. And now the second condition for a subspace is that it must be closed under vector addition. So let's suppose that we have two vectors, let's call them u and v, which are in the null space of A. So that means that A times u and A times v are both equal to the 0 vector, since u and v are in the null space of A. Then let's see whether the sum of u plus v is in the null space. So if I take A times the sum of u and v, using properties of matrix multiplication, this is the same as A times u plus A times v. That is, matrix multiplication is distributive. And both A times u and A times v were the 0 vector. So we have the 0 vector plus the 0 vector, which is the 0 vector. So we've shown then that the sum u plus v is an element of the null space, so it is closed under vector addition. Now the third condition that we have to check for a subspace is that it's closed under scalar multiplication. So here, if C is any scalar and U is some vector in the null space of A, then let's look at whether C times U is in the null space of A. So taking A times the vector C times U, well, this is equivalent to C times the product of A with U. This is a property of matrix multiplication, is the commutativity of multiplication by constants or scalars. So this gives us C times, well, A times U, since U is in the null space of A, must be the 0 vector. So we have a constant times the 0 vector, which is the 0 vector, which means that the scalar multiple C times U is in the null space of A. So since all three properties of a subspace are satisfied, we can say that the null space A is a subspace of Rn. All right. So the null space is an example of a subspace associated with a matrix. Now in our next example, we are given a set W. So we're told here to let W be the set of all vectors in R4 whose coordinates A, B, C, and D satisfy the equations A plus 3B is equal to C and A plus B plus C is equal to D. So here W is the set of these four-dimensional vectors where these components A, B, C, D satisfy the equations that we were given in the problem statement. So here we're supposed to show that W is a subspace of R4 or find an example to the contrary, that is, show that it is not a subspace. So there's a few ways we could go about doing this problem. One way is to make use of our new result regarding the null space as a subspace. So if we rewrite the definition of this set W, we could express it in the following way. So W, I could think of as the set of all vectors A, B, C, D in R4, such that these equations, which are satisfied, I could rewrite in the following way. So my first equation I could write as A plus 3B minus C is equal to 0. And my second equation I could write as A plus B plus C minus D is equal to 0. So if we rewrite W in this way, we see that W is the solution set of the homogeneous linear system whose equations are given here. That is, A plus 3B minus C is 0, and A plus B plus C minus D is 0. So that is, W can be thought of as the null space of a matrix A, where A would be the coefficient matrix whose first row is 1, 3, -1, 0. Those are the coefficients of A, B, C, and D for my first equation. And my second row would be 1, 1, 1, -1. So here W is the null space of a matrix. And by our new theorem, 4.2, the null space of a matrix is a subspace, so W is a subspace of R4. All right. So one note about this example is that the equations which these coefficients had to satisfy were linear equations which were homogeneous. So here it is important in this example that those equations were homogeneous, because if they were non-homogeneous, the solution set would not be a subspace. Why not? Well, any non-homogeneous equation would not contain the 0 vector. So the 0 vector is not a solution of any non-homogeneous system. All right. Now, another way which we could have gone about showing that W is a subspace is to show that it is a space which is spanned by a set of vectors, and then use theorem 4.1 from our last section, which says the spanning set of any set of vectors is a subspace. So how could we show that this is a spanning set, or a set spanned by vectors? Well, let's think about how the vectors in W are defined. So the first two components are A and B. The third component is C, which we are told is equal to the sum of A and 3B. So our third component we could write as A plus 3B. And our fourth component, D, we are told is equal to the sum of A, B, and C. So summing A, B, and C, the first three components of our vector, we have 2A plus 4B. And then this vector can be written as a linear combination of two vectors if we write it in the following way. So we could take a constant A times the coefficients of A from each vector, which would be 1, 0, 1, 2, plus B times the B coefficients from our vector, which would be 0, 1, 3, and 4. So here W is the span of these two vectors. if we were to write this as, say, A times a vector v1 plus B times a vector v2, since A and B are arbitrary real numbers, that shows that W is equal to the span of v1 and v2. And so by theorem 4.1 from our last section, W is a subspace. So that's another approach we could have used here. So in our next example, we have a similar problem. We're given some subset of R3, and we are asked to either use an appropriate theorem to show that our given set is a vector space or a subspace of R3, or find an example to the contrary. So in part A, we have the set of vectors in R3 of the form RST, such that there is the following linear relationship among the components, R, S, and T. So here we have another way to write this as the set of vectors R, S, T, such that if I rewrite my equation, I could express this as 5R minus S minus 2T is equal to 1. So notice that the equation, this linear equation, which is defining the relationship among my components, is non-homogeneous. This solution set of that equation does not contain the zero vector. So here, the zero vector of R3, 0, 0, 0, is not an element of this set W. Thus, W is not a vector space. One of the axioms for a vector space is there must exist a zero vector. Another way we could think about this maybe geometrically is the equation, the non-homogeneous equation, which relates R, S, and T, defines the equation of a plane. So we could say here 5R minus S minus 2T equals 1 is a plane in R3, which does not pass through the origin. So if our plane does not contain the origin, we saw in our last section it cannot be a subspace because it doesn't contain the zero vector. Now in part B, we have a set W of vectors in R3 whose components are involving these real numbers A and B. So here we don't have any equations relating A and B directly. We're told they can be any real numbers. So we could write this space W as the set of all vectors of the following form. So if we split up the general vector into the sum of its A and B components, we can write it as a linear combination, A times the vector -1, 1, 3, and B times the vector 2, -2, -6, such that A and B are any real numbers. So here we have two vectors, let's call them maybe V1 and V2, and we see that any vector in W can be written as a linear combination of V1 and V2, which means that W is the span of V1 and V2. Now, in this particular example, notice one other thing. The vectors v1 and v2 are scalar multiples of each other. So in fact here v2 is equal to -2 times v1. So the span of this set of vectors v1 and v2 is actually equivalent to the span of a single vector v1. Since v2 is already a linear combination of v1. All right. So if we want to see that more formally, we could write W in the following way. It's A times the vector -1, 1, 3. And if I factor out a -2 from my B vector, I have -2B times the vector -1, 1, 3, where A and B are real numbers. But now I could combine this as follows. I could say this is A minus 2B times a single vector, -1, 1, 3, such that A and B are real numbers. And so now we have just some constant multiple of a single vector v1, which shows that W is the span of v1. And by theorem 4.1, we know that the spanning set, or the set generated by a set of vectors in R3 must be a subspace. So W is a subspace of R3. All right. Now, if we'd like to give an explicit description of the null space, we have to go about solving a homogeneous system of equations because of the way that the null space is defined. So in this next part of the section, we'll describe how we could give an explicit description of the null space of a matrix. Now, something that's a little tricky is for any given matrix, there is not an obvious relationship between the vectors in the null space of that matrix and the entries of A itself. It's very difficult to look at a matrix and immediately determine what the null space might be. So we would say that the null space of A is defined implicitly because of the definition. It is defined by a condition which must be checked. So if we have no explicit list or description of the elements in the null space of A being given, then we need to solve the homogeneous equation AX equals to 0 in order to produce an explicit description of our null space of A. So the solution set of that homogeneous equation will give us the explicit description that we're after. So in this first example, we're asked to find an explicit description of the null space of A by listing the vectors that span the null space. And the matrix A that we're given here is this 2x4 matrix. So if we're interested in determining the null space, the first step is to solve the homogeneous equation AX equals to the 0 vector. So let's write that equation as an augmented matrix. So here, the corresponding augmented matrix is the following. So the first row of A was 1, -6, 4, 0. Our second row was 0, 0, 2, 0. And we're augmenting this with the 0 vector since we're talking about a homogeneous system. So we can perform row reduction on this matrix to find our solution set. So here, the first row already has a leading entry of 1 with a 0 below it, and our second row has a leading entry of 2, which I could use to eliminate the 4 that appears above it by taking row 1 minus 2 times row 2. So that makes my first row 1, negative 6, 0, 0, 0. And in my second row, I want that leading entry of 2 to be a 1, which I could get by taking half of the second row, which would make this 0, 0, 1, 0, 0. So this augmented matrix is now in reduced row echelon form. We see that it has pivot columns in the first and the third column. So the second and fourth column will correspond to free variables. So our solution set here can be described in the following way. Using the first row of this matrix, we see that x1 would have to equal 6x2, where x2 is a free variable, since that second column did not have a pivot. X3, using our second row of the augmented matrix, we see 1x3 has to equal 0. And x4 is a free variable. So our solution set, which would be the null space of this matrix, would consist of vectors of the form x, where the first component is 6x2, second component, x2, is free, x3 must be 0, and x4, our fourth component, is a free variable. So these vectors we can write as a linear combination of vectors involving our free variables, say x2 times 6, 1, 0, 0, plus x4 times 0, 0, 0, 1. So if we think about these two vectors, let's give them names, maybe v1 and v2, the solution set for our homogeneous linear system, which would be the null space of this matrix, is spanned by these vectors v1 and v2. So the null space of A can be characterized explicitly as the span of these vectors v1 and v2. All right. So let's look at another one, a similar problem. So here we have a larger matrix, and the problem is the same. We want to find an explicit description of null space of A by listing of vectors that span that null space. So again, if we're trying to find the null space, we're looking for the solution set of the homogeneous equation AX equals to 0, which we could express as an augmented matrix, where the first row of A was 1, 5, negative 4, negative 3, 1. Our second row was 0, 1, negative 2, 1, 0. And the third row of A is all zeros. And we're augmenting that with the 0 vector since this is a homogeneous system. So performing row reduction on this, well, our first row has a lead entry of 1 with zeros below it. Our second row has a leading entry of 1, which we could use to eliminate the positive 5 that appears above it. So our row operation here would be to take row 1 minus 5 times row 2. And this makes our first row 1, 0, 6, -8, and 1, augmented with 0. Our second row is being left alone, and our third row is left alone, all zeros. So the corresponding matrix is now in reduced row echelon form, so we can describe our solution set by looking at the rows of this matrix. So using row 1, we see that x1 is equal to -6x3 plus 8x4 minus x5, where x3, x4, and x5 are all free variables since the third, fourth, and fifth columns did not have pivots. And using the second row of this matrix, we see that x2 is equal to 2x3 minus x4. And as I mentioned, x3, x4, and x5 are free. So our solution set here would be the set of vectors of the form x, where x1 is -6x3 plus 8x4 minus x5. x2 is 2x3 minus x4. And then x3, x4, and x5 are all free. So we can rewrite this vector as a linear combination of 3 vectors where the weights correspond to our free variables. So that would be x3 times the vector -6, 2, 1, 0, 0, plus x4 times the vector 8, -1, 0, 1, 0, and x5 times the vector -1, 0, 0, 0, 1. So for vectors x in the null space of this matrix A, we can write them as a linear combination of these 3 vectors, which I'll call v1, v2, and v3. So here our explicit description of the null space would be the null space of A is the span of v1, v2, and v3. All right. So here we have found a way to describe or to give an explicit description of the null space of a matrix by solving a homogeneous equation and determining the set of vectors which span our solution set. So we can make a couple of observations on the form of our solution set from the last 2 examples. So let's describe these observations. So here, 2 points which we'll want to make about solutions for these types of problems, where the null space of A contains non-zero vectors, and we'll refer back to these later. So the first point that we'll want to make is that the spanning set for the null space of A is automatically linearly independent because the free variables are the weights of the spanning vectors. So none of these vectors, v1, v2, or v3 in the last example, could depend on the other. Otherwise, we would be able to eliminate one of our free variables and write that third vector as a linear combination of the previous 2 free variables. Now, in addition, the null space of A, or if the null space of A contains non-zero vectors, then the number of vectors in our spanning set for the null space is equal to the number of free variables in the equation AX equals to 0. So however many free variables I have that many vectors within our spanning set for this null space.